For 10 years, every gravitational wave detection has told us the same story. Black holes barely spin. Paper after paper, catalog after catalog, the conclusion was consistent. The objects smashing into each other out there in the dark universe are rotating so slowly they might as well be standing still. It became one of the most solid results in modern astrophysics. And 3 days ago, two independent teams on opposite sides of the planet, using completely different methods, published papers on the exact same day, saying the same thing. That result might be wrong, not because the data was bad, but because we accidentally rigged the question before we even asked it. Let me explain what I mean by that, because it's one of the most fascinating statistical traps I've come across, and it has nothing to do with black holes specifically. It has to do with how we interpret weak signals and how a seemingly fair assumption can quietly steer your answer for a decade without anyone noticing. So here's the setup. Since 2015, the LIGO and Virgo observatories have been picking up gravitational waves, these tiny ripples in spacetime produced when two massive objects, usually black holes, spiral into each other and merge. By now, they've cataloged over 150 of these collisions, and from each event, you can extract information. How heavy were the black holes? How fast were they spinning? Were their spins aligned or tilted? Mass is relatively easy to measure. Gravitational wave signals are loud when it comes to mass. The best measurements pin it down to about 2% accuracy. But spin is a nightmare. The effect of spin on the gravitational wave signal is subtle. It shows up as a small correction to the waveform, way weaker than the mass signature. For most events, the data basically whispers about spin. It doesn't shout. And that's where the problem lives. When your data whispers, your assumptions speak. That's just how Bayesian statistics works. You start with a prior, a mathematical representation of what you think is reasonable before looking at any data. Then the data updates that belief. If the data is strong, it overwhelms the prior, and you get a reliable answer. If the data is weak, your answer mostly just reflects what you assume going in. For spin measurements in gravitational wave astronomy, the data has been weak for almost every event. The typical uncertainty on the effective spin parameter is about 0.44. The actual measured value? 0.04. The error bars are 11 times bigger than the measurement. That's not a precise reading. That's a shrug. But the published results didn't look like a shrug. They looked like a finding. Near zero spin. Black holes barely rotate, and the physics community built an entire theoretical framework around that conclusion. There's a model by Fuller and Ma from 2019 that predicts black holes should be born with almost no spin because magnetic fields inside dying stars efficiently transfer angular momentum from the core outward before the star collapses. The gravitational wave data seem to confirm this beautifully. Theory and observation in agreement. Case closed. Except it wasn't the data confirming the theory. It may have been the prior confirming itself. So what is this prior, and why does it matter so much? This is the part that's genuinely clever and a little unsettling. A black hole's spin is a three-dimensional vector. It has a magnitude, how fast it's spinning, and a direction, which way the axis points. That vector lives inside a unit sphere. Any spin state is a point somewhere inside a ball of radius 1. The standard analysis used by LIGO and Virgo picks the spin magnitude uniformly between 0 and 1, just a flat distribution, and the direction randomly over the sphere. Sounds perfectly fair, right? Every magnitude equally likely, every direction equally likely. It's not fair. Think about it this way. Imagine you're throwing darts at a dartboard, but the dartboard is three-dimensional, it's a sphere. If you pick a random radius between 0 and 1 with equal probability, most of your points end up near the center. Because at small radii, there's barely any volume. At large radii, there's enormous volume. The amount of three-dimensional space available at radius 0.9 is vastly larger than the space available at radius 0.1. If you want to distribute points evenly throughout the sphere's volume, you have to pick radii proportional to the radius squared. That's not an obscure technicality. That's a factor of 100 difference. If you draw a radius uniformly between 0 and 1, 10% of your points land below 0.1. If you draw uniformly in volume, Only 0.1% land below zero point 0.1, 100 times fewer. So the standard prior, the one used in essentially every LIGO-Virgo analysis for the past decade, is piling probability near zero spin before the data even arrives. When the data then comes in and says almost nothing because the signal is too noisy, the final answer just reflects that pileup. Zero spin. Not because the universe said so, because the math was set up that way. The new paper by Vaishak Prasad and B. Sathyaprakash at Penn State puts it bluntly. The data do not require vanishing spins. The prior does. Now, Sathyaprakash is not some random voice. He designed the matched filter search algorithm that LIGO and Virgo still use today. He co-authored the landmark paper on the very first gravitational wave detection, GW 15914. He's a fellow of the American Physical Society and one of the architects behind next-generation detectors like Cosmic Explorer and Einstein Telescope. When someone like that says the field's default statistical tool has a structural bias, people pay attention. But what really makes this moment unusual is what happened on the other side of the world. On the exact same day, February 13th, 2026, a completely independent team at the University of Tokyo, led by Kazuya Kobayashi, posted their own paper attacking the same problem with a totally different approach. Instead of redefining the prior in three-dimensional spin space, they proposed a prior that's uniform in the two quantities gravitational wave data can actually measure, the effective spin and the precessing spin, and they found the same thing. The standard prior assigns essentially zero probability to spin configurations where both black holes are spinning aligned with the orbit, which is exactly what isolated binary evolution predicts should be common. Two groups, different countries, different methods, same conclusion, same day. When that happens in science, the odds that both are wrong go way down. This isn't a lone provocateur making a splash. This looks like a field reaching a tipping point. So what does the reanalysis actually show when you apply the corrected prior? Prasad and Sathyaprakash tested it on three specific events. First, GW 15914, the original detection from 2015. For that event, the data is so uninformative about spin that both priors give you essentially the same answer, which is actually the point. When the data can't tell you anything, whatever your prior assumes is what you get back. The old prior assumed near zero, so it returned near zero, not a measurement, a mirror. For a more recent event, GW 23814, where the signal carries a bit more spin information, real differences start to appear. The volume uniform prior shifts the posteriors noticeably. But the most dramatic case is GW 25114, the clearest binary black hole signal ever recorded, with a signal-to-noise ratio of about 77. With the old prior, you get the familiar low-spin answer. With the new prior, the analysis lands in an entirely different region of parameter space, a high-spin region, and the data actually slightly prefer it. The log likelihood is marginally higher there. The data were trying to point toward higher spins, and the old prior was pulling the answer away from what the signal was saying. And there's a second trap that makes this worse. You might think, okay, so the prior was a bit off, but we can just reweight the old results after the fact. Statisticians do this all the time. You take your existing samples, multiply by the ratio of the new prior to the old one, done. Except that only works if you actually have samples in the region you're trying to reweight toward. If the old prior suppressed high-spin regions so aggressively that the sampler never explored them, there's literally nothing there to reweight. You're multiplying zero by a big number, and you still get zero. Prasad and Sathyaprakash show this is exactly what happens for GW 25114. The reweighting from old to new prior completely misses the high-spin posterior mass that the new analysis finds. They estimate you'd need at least 10 times more sampling points to cover that region under the old prior, which they say is computationally impractical for a catalog of hundreds of events. So reprocessing isn't as simple as running a quick fix. You'd potentially need to redo the parameter estimation from scratch for every event in the catalog. Now, why does any of this matter beyond statistics? Why should you care whether black holes spin at 0.05 or 0.3? Because spin is a fossil record. It's a compressed memory of everything that happened to a black hole before we detected it. How the parent star died, how angular momentum moved through its interior, Whether the black hole grew by swallowing gas or by merging with other black holes, whether it formed in isolation with a partner or was randomly paired up in a dense star cluster through gravitational encounters. Different formation stories leave completely different spin fingerprints. If black holes really have near-zero natal spins, that strongly supports the Fuller-Ma model, where magnetic fields inside massive stars efficiently drain angular momentum from the core before collapse. That model has been the dominant framework for 6 years. But if spins are actually moderate, say 0.2 to 0.4, that picture cracks. You might need tidal spin-up from close binary companions or chemically homogeneous evolution, where rapidly rotating stars in tight pairs evolve completely differently. Or the angular momentum transport physics inside dying stars might just be less efficient than we thought. And it goes further than just astrophysics. Tests of Einstein's general relativity use black holes spin directly. When two black holes merge, the remnant rings like a bell at very specific frequencies determined entirely by its mass and spin. That's the no-hair theorem. The entire promise of testing whether black holes match Einstein's predictions rests on knowing what the spin is. If the input spin estimates are biased by a prior artifact, every test of general relativity done with gravitational waves might need a second look. There's also the dark matter connection. There's a theoretical process called black hole superradiance, where ultralight particles, a dark matter candidate, can extract energy from a spinning black hole and slow it down. If we measure high spins, that constrains how heavy these hypothetical particles can be. Higher measured spins mean tighter constraints, means fewer places for certain dark matter candidates to hide. A systematic underestimate of spin means we've been too lenient. And then there's pure energy. A spinning black hole is the most efficient energy source in the universe. Through the Blandford-Znaiec process, spinning black holes power the relativistic jets we see blasting out of quasars and active galactic nuclei. The faster the spin, the more energy available. A maximally spinning black hole can convert up to 40% of infalling mass into energy. Nuclear fusion manages 0.7%. If stellar mass black holes are spinning faster than we thought, the universe is a more energetic place than our models currently account for. To give you a sense of scale, at maximum spin, a black hole's event horizon rotates at the speed of light, 300,000 kilometers per second. The stellar mass black hole GRS 1915 plus 105 in our own galaxy spins at roughly 1,150 rotations per second. And the supermassive black hole in NGC 1365, a thing larger than twice the distance from Earth to the Moon, has its event horizon moving at 84% of light speed. These are real measurements from X-ray observations. Black holes are capable of extraordinary rotation. The question has always been whether the ones we see merging via gravitational waves are spinning that fast. And now we're being told that maybe the answer was never as settled as we assumed. But let's be honest about what this paper does and doesn't do. It doesn't prove black holes are spinning fast. What it proves is that the standard analysis was structurally biased toward finding low spins, and that when you correct for that bias, the data are compatible with a much wider range of spin values. That's a big distinction. The universe might still turn out to prefer low spins, but we'd need the data to tell us that, not the prior. The paper itself is a short letter, not a full catalog reanalysis. They demonstrate the effect on 3 events, not all 153. A complete reanalysis of the entire catalog with the new prior hasn't been done yet. They acknowledge this and say detailed injection studies are underway. There's also a real methodological debate to have about whether hierarchical population models, which combine information across many events, are already robust enough to overcome single-event prior biases. The LIGO-Virgo-Cogra collaboration's official population analysis uses exactly these hierarchical methods, and proponents would argue that any single-event bias gets washed out when you fold in the whole population. Prasad and Sathyaprakash counter that if the sampler never explored the high-spin region for individual events, there's nothing for the population model to work with. That argument hasn't been settled yet, and physically agnostic is itself a choice. Uniform in volume sounds neutral, but if astrophysics genuinely produces mostly low-spin black holes, then a volume uniform prior would be wrong in the opposite direction, overweighting high spins. The true answer probably lies somewhere between the two priors. Nature doesn't care about our definitions of fairness. Still, the convergence of evidence is striking. Prasad and Sathyaprakash found the prior bias in three-dimensional spin space. Kobayashi's group in Tokyo found it independently in effective spin space. Earlier work by Adam Siewicz and collaborators last year found no support for a subpopulation of truly non-spinning black holes, and actually found a normalization error in previous analyses that had inflated the evidence for non-spinning systems. Callister and colleagues back in 2022 had already argued that a majority of vanishing spin black holes wasn't required by the data. This isn't one paper making a bold claim. It's multiple independent threads all pulling in the same direction toward the conclusion that we've been overconfident about low spins. The next generation of detectors will end this debate for good. The Einstein telescope in Europe and Cosmic Explorer in the United States will detect mergers with signal-to-noise ratios up to 2700. At that level, the data is so overwhelming that priors become irrelevant. Whatever you assume going in, the signal drowns it out. We'll actually know how fast black holes spin instead of guessing through the fog of weak signals and hidden assumptions, but that's years away. Right now, the field is sitting with a fascinating and uncomfortable question. How much of what we thought we learned about black hole spins over the past decade was actually the universe talking, and how much was us hearing our own echo? Because that's what this really comes down to. Not a story about black holes, a story about how easy it is to mistake your assumptions for evidence when the signal's just quiet enough to let you. A math error that didn't look like a math error, a bias that disguised itself as a discovery, and two teams on opposite sides of the Earth who noticed it on the same day. Want more of the latest science that challenges what we thought was settled? There's always another assumption waiting to be questioned.